Hi everyone, this is Matt Touchot and Intro Stats, and today we're looking at a problem from my book, Introduction to Statistics for Community College Students. This is number 21 in section 3F. So this is a one population mean average hypothesis test, and again this is the first time we're really putting hypothesis tests together. We've been learning about all these different facets of a hypothesis test, and what these numbers mean, but we've never really put it all together. So these are problems where we're trying to put a hypothesis test together from beginning to end. All right, so let's look at the number 21. Mike wants to know the average price of a hamburger. Okay, he randomly selects 24 restaurants and recorded the price of a hamburger. The sample mean price was $3.88. and the sample standard deviation was $1.14. A histogram of the data is below. Does this data set meet the assumptions necessary to perform a hypothesis test? If so, use a 10% significance level to test the claim that the average price of a hamburger is greater than $3.50. So is the average price of a hamburger greater than $3.50? Okay, so let's take a look. So we want to start with try to figure out what the null and alternative hypothesis would be, right? That's where you always start. So we start with the claim. What's the claim? It says here that the claim is that the average price of a hamburger, and we are using mean averages, not medians or another type of average. So this is a mean average problem. Even though it just says average here, we are using means by the context. Okay, so the mean average price of a hamburger is greater than $3.50. Okay, so let's see if we could write that down. So let's see, what would that be? So mu, remember population mean, we use the Greek letter mu, looks like U with a tail, is greater than $3.50. Remember, greater than looks like an arrow pointing to the right, and that's my claim. Okay, so what would be the opposite of that? Now that's interesting. The opposite of greater than, if it's not true, actually is less than or equal to. So we could do a less than or equal to, or you could do equal to as the opposite. If we did a less than or equal to, that would be fine as well. It doesn't really matter. The HA. So this could be a greater than or equal to, or you could just have an equal to here. We'll kind of look at that in a second here. But again, now once we have these written down, the claim, what they think is true, and then what is the opposite of what they think is true, or what's the opposing view. Now we decide what's H0 and HA, right? So remember, H0 has to have an equal to part. So whichever of the two has an equal to part, this less than or equal to would have to be a null hypothesis because it has an equal to part. Greater than does not have an equal to part, so that would have to be an HA. So if we look down here, looks like they wrote it as mu is greater than $3.50 is my HA. Notice that's the claim. And then mu is equal to $3.50 as the null. Again, you could have written less than or equal to. Either one's okay. Most people in stats like to write equal to instead of less than or equal to. Remember, it doesn't really matter because it's still going to be a right-tailed test. Notice that the greater than is the HA. Remember, the symbol in HA tells you the type of test, so greater than points to the right. So this is a one population mean test. And it is right-tailed. We got a right-tailed test because HA determines the test. Okay? All right, so now what about our assumptions? So what would be the assumptions for a one population mean average test? Well, let's go back to the problem here. Again, we would want random. Were these randomly selected? It says he randomly selected. Now we can, I always talk to my class how a lot of people out in the world say they randomly collect data, but they don't really even know what random data really is. So we're going to assume that Mike actually knows what random data is here. So we're going to assume that it really is random data. Now, if it's a random sample, small random sample of 24 restaurants out of, thousands of restaurants, we're probably okay with independence. We're not going to accidentally get two restaurants that are the same restaurant or the same owners or things like that. If this is a small random sample out of a very big population, we're probably okay with independence. So random and independence, we're probably okay. And then how about this one? Now, with the other, for a mean average test, remember it's 30 or normal, at least 30 or normal. Now remember, that's an or assumption. One of those two things has to be true. It has to either be normal or the sample size has to be greater than 30. Problem is our sample size was 24. So that is not greater than 30. So this would be too small of a data set unless the data is normal. Well, that's why they provided a histogram down here. They want you to check it. Does it look like this is bell-shaped? Actually looks pretty bell-shaped, right? You got the highest bar in the middle, and we got about an even symmetric tail going to the right and the left. Okay, so it does look relatively normal. So I think we're going to pass the 30 or normal. Remember, it doesn't have to pass both. Or means one or the other. So even though it was not 30, it was normal. So it's going to pass the 30 or normal requirement. Okay, so it passes all the assumptions. So I guess we can move on with the test. So let's take a look at our test statistic here. Our test statistic, by the way, this is a t-test statistic. This would be a t-test, is 1.633. So this means that my sample mean, 3.88, $3.88, is 1.633 standard errors above the number in the null hypothesis, 350. Okay, remember the Z and T test statistics tell you the number of standard errors that the sample statistic is from that number, that parameter in the null hypothesis. Okay, so if we were writing a sentence for this, the test statistic would be the sample mean was 1.633 standard errors above, remember because it was positive, it's above the population mean of 350. Now is that significant? Well, we have to look at the critical value. This was a right-tailed test. Where does the tail start? Critical value right here. It says the tail starts at 1.32. Okay, so think of it like a right-tailed test, right? We got a curve, and the right tail starts at 1.32. So anything to the right of that would be considered significant. So 1.4, 1.5, 1.6, 1.7, 2, 2.5 would all be significant. 1 or 0.9 would not be significant, right? Because that would not fall in the right tail. So 1.633 does fall in the right tail if your critical value of your tail starts at 1.32. So that tells me that this is significant. So the $3.88 actually significantly disagrees with the null hypothesis. The sample data significantly disagrees with the null hypothesis. All right, how about our p-value? Could this data just be the result of sampling variability? Why did my sample data disagree? Did it disagree because this $3.50 is wrong? Or did it disagree because all random samples disagree? We call that sampling variability. Well, again, look at your significance level, 10%. My p-value was 0.058, right? 0.058. What's that as a percentage? Hopefully you said 5.8%, right? That's not 58%, it's 5.8%. So 5.8% is actually lower than the 10% significance level. So we have a low p-value if we're using a 10% significance level. Okay, so this would be considered a low p-value, meaning it's unlikely to be sampling variability. So the reason that this sample data disagrees with the null hypothesis is probably not sampling variability. It's more likely that the $3.50 is wrong. So as we know, a low p-value allows us to reject the null hypothesis if it met all the assumptions. So this met all the assumptions, and we have a low p-value, so that is considered significant evidence. And it's also, again, allows us to reject the null hypothesis. So let's go back to our problem here. So again, our p-value sentence, if the null is true and the population mean average is $3.50, there's a 5.08% probability of getting the sample data or more extreme because of sampling variability. All right, let's take a look here, 1 second here. Ah, I have a typo there. It's the p-value is actually 5.058. Oh, not 0.0508. I'll go back and fix that later. So it should have said 5.80, not 5.08 there. So that was a typo there. All right, I'll have to fix that later. All right, since the p-value is less than 10%, it's unlikely to be sampling variability. We rejected the null. It met the assumptions, and we have a low p-value, so that is significant evidence. So there's significant evidence to support the claim. Remember, we rejected the null, but the claim was HA. The claim was the opposite. So if you say the null's wrong, you're kind of saying the alternative is correct, right? Or we think we're at least supporting it. There is significant evidence to support the claim that the population mean average price of a hamburger is greater than $3.50. So Mike's claim that the average price is more than $3.50 is probably could be true. Okay, we have some evidence to back him up. All right, so that was section 3F, number 21. I hope that's helpful for you.